Let's go.
All right. Well, thank you everyone for having me. This is definitely going to be a fun presentation. I wanted to do something more along the lines of motivating effect systems. And effect systems are, it's not a term I'm going to use actually throughout much of this presentation. But it's generally describing systems like Cat's Effect, Zio, Tokyo, things like that, which have come a little bit more into vogue within the last few years, and I think have started to really make a case for themselves as the next step for the reactive paradigm. Um, so I want to talk about why this is the case, because there are some pretty obvious drawbacks that you can see on the surface to effect systems and the way that they're encoded in particular. And it's difficult to see the motivation for why people are choosing them until you actually break it apart. It's one of those things that doesn't fit very well on a slide. Just so you have an understanding of my background and my biases here, I have been working on Cat's Effect for, I don't know, 5-7 years, however long it's been. I worked on Scala's Stream before that. So I am going to be primarily talking about Cat's Effect here, but pretty much everything I say is applicable to any effect system. I work at Disney Streaming, so I deploy services at absolutely enormous scale around the world. So performance and scalability and sort of practical applicability and scalability within an organization and dev team is something that I think about a lot. And I think everything is very much grounded in that truth. So to that end, I want us to have in our mind, as we kind of go through this presentation, this type of archetypical use case. Okay, now specifically what I'm talking about is a typical microservice. Someone makes a request, we decode it probably as JSON. That in turn leads to a couple other requests that maybe we make in parallel or something like that to some downstream services. We bring back that data, gather it back together, re-encode the response as JSON, and then send it on our way to the client. This right here describes probably 90% of what people do on the JVM. And there's a good reason for that. The JVM is actually very, very good at this specific pattern. And effect systems in particular lean into this and try to make this pattern better by solving some of the core problems associated with this type of application. So in order for us to really talk about how that happens, we need to talk about what those core problems are. And in particular, what we're going to talk about are scarce resources. Okay. So scale is always about managing scarce resources, right? Like you're trying to run a service that maintains tens of thousands of RPS on a single node or something like that, and you have limited resources in which to do that. You certainly don't have tens of thousands of CPUs, for example, right? You don't have tens of thousands of gigabytes of memory, or at least you probably don't. Certainly not per node. You don't have tens of thousands of file handles, or actually you probably do, but probably not any more than that. So these are scarce resources that are generally bounding factors in scale. And this is the reason why when you scale out services, you generally set up scaling signals in sort of your container cluster or something like that. Based on one or more of these triggers, you generally monitor these things and alert on them. You generally watch these things in load tests. You work to optimize these types of factors because this is exactly what you care about optimizing. This is exactly what is your limiting factor in terms of achieving higher scale, even when you're scaling out. Like this type of stuff matters a lot. One of the ones that we don't think about as much as being a scarce resource is actually threads. Now, there are a lot of other scarce resources, things that are not on the screen, but threads are the one that I'm going to talk about right now because they're really underappreciated. And one of the reasons they're underappreciated is they're only a scarce resource because of some details of how they are implemented. But the bottom line is basically that if you are working with threads, you really can only have a few thousand of them in a singular JVM before things start going bad. Realistically, the limit is like before that, and then the hard limit is like quite a bit above that. You're just going to start seeing thrashing increase as the count rises, particularly when you have threads with workflows that have some overlapping working set, other things like that make it difficult for the GC to sort of understand it. And really, when you're looking at sort of end-to-end metrics, you're generally going to see this in terms of pause times. So I've seen systems that got backed up on, you know, mid 8 to 9,000 threads, something like that, on a single machine. I think it had 4 vCPUs or something like that, and the pause times were horrendous, like 15, 20 seconds. That order of magnitude. It was really, really, really bad, which obviously is untenable. Like you have to kill the node at that point. So you can't have a ton of these things for various reasons. You also can't allocate them very quickly. So it's not like you can sort of have a thread and then throw it away really fast and then get another one, like that type of thing. You certainly cannot make these things on a per request basis, because if you do that, it's just going to take you way too long to respond. Like if you're doing a tier 1 service, you really have to respond in sort of tens of milliseconds, hundreds of milliseconds at the absolute most. And if you're trying to do that for hundreds or thousands of connections simultaneously, the allocation pressure alone will murder you. So threads are really, really special, but they're also special not only for all of these reasons, which come from the kernel and from the JVM itself, but also from another subtle reason, which is basically a limitation of the JVM as a platform. And that is they are our only way to influence CPU affinity. Now, CPU affinity is not a concept that we tend to think about very often, but that's a little strange because the impact is extremely high. So let's kind of unpack what this is. So physical thread counts on most deployment scenarios are really, really low. This is particularly true if you're using containerized systems like Kubernetes or ECS or something like that. What I mean by a physical thread is like what we generally call a vCPU. If you're on a bare metal, it could be a core, but it's more than just a processor, because processors often have hyperthreading enabled, which doubles the number of physical threads that you can have in your system. So really, the physical thread is just about this is a thread of execution which is entirely parallel when executed with the other physical threads on the system. So my system right now, for example, is an 8-core machine that has hyperthreading enabled. So I have 16 physical threads. The box sitting next to me has 24 physical threads, things of that nature. Now, ideally, each thread would map directly to a single CPU forever. Like you just put a thread on a CPU and you have it there always. This is obviously not possible because the kernel needs to do some work, the just-in-time compiler needs to do work, the GC needs to do work. You have other things that are kind of coming along, other processes on your system. But like by and large, if we narrow the scope to just the part of your application which is most active and most influential on the load on the system, those are your active threads, and those are what you would ideally, each one would map to a single physical thread underlying, and you would never move them. Why would you never move them? Because of page faults. Okay, so when a single thread is sitting on a CPU, it's taking advantage of sort of modern process architecture at extreme depth. And we'll go into what this means in a second. But ultimately, every time you have to evict a thread, or rather every time the kernel evicts a thread from a CPU, every time it moves it off of a physical thread and maps some other virtual thread onto it, the result is usually that those pages, the memory pages that have been pulled into the cache, get blown away. And this is actually a lot more expensive than anybody seems to think it is. I have measured in production scenarios, page faults alone being over 30% of the total runtime of the application. It is staggeringly costly. Now, this is a little bit of an outlier, but like you're still going to see this as a very, very significant factor in any top line metrics. I think the only reason people don't tend to think about page faults as much is because it's not very visible. You don't realize it's happening. It's harder to measure. There's not a lot of good reporting on it. But believe me, this is a real problem. And the only way to avoid it is to try to like narrow things down to specific CPU affinity. Specifically, you want to align your active thread count to the physical thread count on your underlying system, where active thread is like, this is a thread that's doing a lot of compute. Like this is the thread that's doing a lot of work. So we can kind of illustrate this problem graphically, because it really is incredibly important to understand this, because this is the root of so many things that kind of cascade after it, so many design assumptions and so many elements of the reactive paradigm. So imagine that you have this type of situation where we have two physical threads, two processors. And we have 5 threads in the application space that we're trying to map down to it. So the way that this generally works is like the kernel is going to take care of like putting the code on the processor, and will take care of putting the working set into the cache. So what does this mean exactly? Let's unpack this. When a thread is running, it's not like it's just doing math like in place with data that's in the registers. I mean, it might be if you're doing like something like machine learning or matrix multiplication, but then I would ask why you're not using a GPU. Like most realistic threads, again, in kind of the microservice paradigm, have some sort of memory state that they're working with, like things that are values, objects that you're carrying around, data within those objects that you're referencing transitively, et cetera, et cetera, et cetera. This is the working set of the thread. And anytime a thread takes a step forward on the processor, it has to load that data and access it. And this requires pulling it through the caching hierarchy of the system. And the way that the caching hierarchy works is it kind of makes the assumption that if instruction number 1 accessed a piece of memory, then instruction number 2 is much more likely to either re-access that piece of memory or access some memory that's near it. Okay, so all of modern hardware design is kind of predicated on this type of assumption. And in practice, it works very, very well. As long as that thread is sitting there, you're good. And while we're doing this, right, like there might be another thread that, say, thread 4, that's mapped to the other processor. And these threads are just kind of running. They're on the CPU, they're doing their thing. The other threads are suspended by the kernel, waiting for their turn. But what will inevitably happen here is the kernel is going to make the decision in its scheduler to move one of the other threads onto the processor. And when this happens, it will preempt the running thread and evict it from the core. The problem is when you do this, it effectively wastes all of that work that it did pulling memory into the cache hierarchy. Because let's say that thread 2 has to get brought down and put onto that processor, the working set for thread 2 has no particular connection to the working set for thread 1. And so you're going to have a cache miss. It's going to have to blow away the caches and reload from main memory just in time for the thread to execute for a little bit and then get preempted again for something else, say thread 5. This is why page faults can be so costly. As your thread counts increase, you have this sort of jostling that happens. It's like the kernel scheduler is constantly trying to get them onto physical threads. And in so doing, it ends up evicting and evicting and evicting. And you basically defeat all of the optimizations that are in the processor. In fact, in some cases, if you do this to such a significant degree, you can actually make it so that those types of cache hierarchies are actually a net negative on your performance. Because again, all optimizations are assumptions and you're violating those assumptions. The only way to really get yourself out of this scenario is to make sure that the kernel scheduler is not trying to jostle threads around between processors, but instead you have an exact mapping between the threads that you're trying to use and the physical threads of the underlying hardware for the most part, right? Again, like there's other stuff going on. And when that happens, the kernel scheduler will very, very happily keep you affined to a single processor, which reduces your page faults dramatically and really, really significantly increases performance. So this is the ideal. And this idea, this thought, is behind almost all of the advice I've ever given anyone on how you should map out your threads. But for the purposes of like what we're talking about here, let's just try to remember like this paradigm, this idea, this goal to optimize for is highly impactful and something that has some fairly profound effects. And in particular, it makes threads an even scarcer resource than they would have otherwise seemed. So we've said that we couldn't allocate thousands of them. Now, because of page faults, not only can we not allocate thousands, we probably have to stick to like single digit type thread counts because that's the number of physical threads, the number of vCPUs that we're probably working with. So these are a really, really scarce resource. We have to be very, very careful with them in order to preserve this property and keep our context switch penalties very low. In tension against all of this, though, is the fact that we have many semantic processes that we are trying to execute. So if we assume, for example, that we're trying to target 10,000 RPS on a single node and 50 millisecond response times. These are very typical metrics for a high-scale tier 1 service. That means that we need to average about 500 concurrent connections at any point in time. It's going to fluctuate above and below that, but like that's roughly speaking what we have to be able to do. Allocating that number of threads is possible, but really, 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 really slow. Like again, we have the GC root problem. We're going to have that context switch problem with the sort of page faults, all that type of thing. Ultimately, we won't want to be in this situation at all. Instead, what we actually want to do is multiplex many connections across a small number of threads. And those threads then can stay pinned to the cores, and then connections kind of move in and out of them. This is, for those of you who know the literature, this is basically an MN scheduler, right? This is the same problem that the kernel is trying to solve by mapping threads down to processors. We're trying to do that by mapping connections down to threads. So all systems at scale have to solve this problem. If you're not solving it with threads, you're solving it with something else. And the more efficiently you can solve this problem, the better you can scale. This is a huge, huge factor in practice, really, really huge. So then a lot of the space of JVM optimization, especially modern JVM optimization, then revolves around achieving this goal as efficiently and as effectively as possible. And the main lever we use to get there is asynchronous programming. So asynchronous programming kind of comes from this type of observation, which is that you're trying to multiplex connections, like many, many connections across a small number of threads. And your connections are basically I/O operations, right? Like you're basically reading some bytes from a thing. So maybe input stream. But how do you multiplex input stream? Like the read function promises to return bytes to you. It promises to actually hand you some bytes, and your control flow doesn't increase or doesn't continue until those bytes come back to you, which means that the calling thread, whoever calls read, has to sit and wait and do absolutely nothing while the input stream is talking to the network or talking to the disk or doing whatever else it happens to be doing. This is incredibly wasteful, right? Because the thread literally can do nothing. You can't multiplex multiple input streams onto a singular thread. You really would need a thread per input stream, which gets us all the way back to like the fact that we can't have 500 threads managing these types of connections. So it wastes a very, very scarce resource to do these types of blocking calls. And this is particularly bad for that scatter gather workflow that we were thinking about, right? It's so bad for scatter gather, particularly because when, if you take the archetype of like the request comes in, well, that's an IO action. So I guess we could block a thread on that, but like, so for the sake of argument, let's say we do, we block the thread, we get the bytes, then we go and decode them. Okay, everything is fine. This is all in the CPU. And then we go to make these downstream requests to like our downstream services. We have to block the same thread again to make those requests. And if we want to do that in parallel, which is usually what you want to do with scatter gather, you actually have to block 2 threads per incoming request in order to achieve that same paradigm. So you're wasting a lot of resources and you're kind of blowing away all of these optimizations that we're trying to achieve. So with asynchronous programming, the solution is basically event loops. Okay, so this is very similar to any other evented paradigm, sort of listeners and callbacks and things like that, right? The idea is basically you have a single thread or a small number of threads which pull the kernel for all outstanding IO events, like not events that are specific to a certain connection, but rather any events that are anything, reads, writes, failures, all that jazz, like all of it gets pulled together and batched up all at once. This then in turn means that if you're another thread that wants to initiate a read or initiate a write, all you have to do is register an event with the kernel and then move on. And then at some point, that polling thread is going to get the response from the kernel. The kernel is sort of managing all of this. You get the response using the kernel and will fire a callback that will continue your semantic thread of execution. So ultimately, it requires you transform your code from return-oriented to callback-oriented. The benefit here really is that threads are free to work on other connections while awaiting results. So you don't have to sit there, wait for a particular response, and then move on. You're allowed to sort of register your callback and then be like, okay, I'm going to work on one of the other 500 connections that I care about right now. And then eventually when that callback comes in, I'll get to it in order. So it's a little bit like it's kind of achieving that multiplexing paradigm. But the downside is that you need to rewrite your code. And so you need to take your program that's sort of in this type of paradigm where you have a foo function that returns an int to you, right? It doesn't let your control flow continue until you have the int in your hand right now. And you have to rewrite it into this type of form. So now instead of returning an int, foo returns a unit, but it takes a callback that you hand an int to. So these two formulations are actually equivalent in terms of expressive power if you ignore sort of multi-calls, but they are radically different in terms of how the scheduler is capable of working with them. Because the foo function returning a unit as opposed to returning an int means that the thread is allowed to register that callback and then move on and do completely different things. And then at some point the callback fires, maybe comes back to the same thread, maybe comes back to a different thread, and is able to pick up that same semantic action. So this is how you sort of solve this problem. This is called the CPS transformation, if you ever hear that term. So it's a paradigm shift. And it's a paradigm shift, particularly as you start thinking about sequentiality, right? Like you want to encode this notion of, I do a thing, like I read the body of a request, and then I do another thing. I parse it, and then I do a third thing. I make a call to a downstream service. This is a sequence of actions. When you encode this on a thread using blocking I/O, then you would encode that basically with semicolons, right? Like, statement, 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 statement. This is asynchronous as a paradigm shift where instead of thinking about strict sequentiality in terms of statements, you have to think of semantic sequentiality, where like I did a thing, and then after that, at some point, this other thing happened. And then after that, at some point, this other thing happened. Callbacks encode this. They encode this notion of semantic sequentiality, but without using throw and return. So it kind of gets us what we want, at least in some sort of high level sense, but it's really, really, really ugly. And in particular, it's ugly because most programs involve a lot of this. So realistically, you're not just going to call one foo that gives you an int and then that's it. You're probably going to call a lot of them. And this is what unhappy Node.js developers fondly refer to as callback hell. You're going to do this like constantly if you don't have a better approach. And as this paradigm began to catch on in the industry, I think the urgency around devising a better approach became a lot more significant. And that's what starts moving us towards something that in the effect system world we call fibers. But we're not quite there yet, right? We just have to sort of like take baby steps here. So the solution that was adopted by sort of the JavaScript world for Node.js and really lit a fire under the reactive paradigm in Scala and in Kotlin and in other languages is Future. So Future is basically as a thing, it's a singular thing that represents a callback which hasn't yet been completed. Technically, Future could also represent a callback that is completed, but that's a little bit of a degraded case, right? It's fundamentally about the callback. And the nice thing about Future is that by making it a singular thing that, will represent the production of this A value, you're able to take advantage of a lot of other things in the ecosystem that we understand how to compose together. And in particular, it forms a monad. So Future forms a monad, which allows us to flatten our sequences, which had been kind of nested into this callback hell. It allows us to flatten them into a linear chain. This is actually the only thing that monad promises you. Like this right here, this is the reason monads are interesting. Very concretely, rather than saying like flat map and then inside of that flat map and then inside of that flat map, which is basically what callback hell is, we can instead say flat map and then sequence with it flat map and then like do these things kind of back to back to back to back to back, just sort of flatten it out. This is the associativity law of monad. And literally this is like the big thing that Future gives you. It's the big thing that monad gives you in general. And it takes away callback hell. Because now instead of having this sort of deeply nested chain that kind of like propagates through your entire application, now you can have something a lot nicer like this, where it's just, okay, we do the foo, then do the bar, then do baz, then do quux. Like these things are very visually sequential. They're very visually linear, kind of like what we had when we were programming directly on threads with statements and such. But under the surface, there's going to be callbacks firing between each of these steps and other things like that. So as soon as the industry started to get these types of tools, which really were designed to get us out of the problem of like manually fiddling with callbacks and other things like that, that started everyone down this path of having more and more and more of your application, more and more of your code, more and more of your library ecosystem in terms of this type of abstraction, because this is very fundamental. And if you wanted to have a part of your program that was compatible with this kind of callback suspension, compatible with moving between threads, compatible with fairness, which is not even a thing I'm going to talk about very much, but it's important. You started moving more and more of your code into future. And that sincerely gets quite annoying. Anyone who's worked on a really, really large code base in Scala, especially some years ago before there were really any alternatives, we've all kind of done this where we've put the entire program in future in some way. And it does start to get very hairy to diagnose what's going on. It's certainly very difficult to test. One of the biggest questions you find yourself asking all the time is the future running or isn't it? Like, is this callback completed? Is this callback a thing that's going to start if I like do something to the future, or if I do something somewhere else? What exactly is going on here? Like having a future of string, for example, or a future of bytes in your hand doesn't mean very much. It means that you can like flat map on it and it'll give you bytes eventually, but you can't reason about what's going on. You can't reason about your control flow. And this leads to some really, really unpleasant cases, especially when you build this large application, then you try to maintain it, you try to refactor it, you try to evolve the code. Even very, very, very simple changes can pretty dramatically change the meaning of your code. The classic example of that is here, right? Like take this sequence, okay? And then what if we transform it into this? Okay, we took baz on the left and we just pulled it out into a variable. This is not the same program. Because if baz performs some sort of side effect, right? Like maybe it commits in a database. Well, it's now doing that probably before foo and bar have a chance to run. So we've changed the way that this works. And when you come from imperative programming, it seems somewhat intuitive that this would be the case. Like we were sort of taught to be aware, of these types of cases. But when you fan it out to a larger code base, this type of restriction, especially as it scales out, gets really, really hard to live within because you have to think so carefully about like this, then this, then this, then this, and this. You can also run into like serious problems with memory leaks, right? Like what happens if you call baz, which starts a future running, and that future at some point is completed, but you don't need the result anymore. Like you still have a reference to baz somehow, but like you're not actually using it in the application. Or maybe you close over it and you haven't received another callback. Maybe bar hasn't completed yet because it's taking a long time. Well, you're holding onto the memory associated with the response to the baz callback that whole time. And this is also a problem which shows up in large future-based code bases. It's just sort of a thing we tend to live with because it's better than callbacks, and it is better than callbacks, but it's still really annoying, and it's definitely not the type of thing we would want to do if we had a choice. So these types of refactorings become hard, which gets to maintainability. You also just kind of don't get a lot of benefits from it aside from getting out of callback hell. Like basically future is designed to do one thing very, very well. It's just flatten out callbacks into a linear sequence. That's it. And it does do that job. It does it exceptionally well with a minimum amount of boilerplate and performance overhead, but it doesn't give you anything more than that. And I have some really good examples as to like what this means, but I don't think we should have to settle for this. And effect systems are basically the observation that we don't have to settle for this. So when I talk about control flow, I talk about things like this happens before that. We already kind of gave an example of like how it's difficult to be certain of what's going on, like moving that baz thing around. What's funny is I kind of threw up a bit of a false flag with that on the previous screen where I was like, okay, here's a transformation. Now the program is not the same. The program might be the same in that it might actually do the same thing. It might actually produce the same result. We don't actually know unless we look at how BAS is defined. So it's hard to be sure that even I gave you a valid example, because without knowing everything about the program, you can't know whether or not that simple example actually makes any sense. That feels very broken. That feels very uncomposable, feels very difficult to maintain. This type of limitation expands out in some surprising areas as well. So control flow is a lot more than just sequentialization. Really, you want a lot of other power as well. Like you want the ability to short circuit with errors, which Future actually gives you because it is so fundamental. You also probably want the ability to do something like timeouts, right? You don't want a request to come in and just sort of spin there for hours and hours and hours. If it's not working, like if the sort of upstream is not responding, maybe you should just time it out and throw away those resources. Well, with Future, you actually have to encode that manually, like usually like some sort of shared Boolean flag or atomic Boolean or something like that that you set, which represents like, okay, stop doing stuff now. Things like that are really, really difficult, and they're exceptionally common cases. Like these just happen all the time. Back pressure is entirely left as an exercise for the reader. And this is something that bothers me a lot. So back pressure ultimately boils down to your system's ability to be elastic while under pressure, right? Like as your system undergoes more and more and more pressure, some components of the system will slow down before other ones. Some will start reaching their resource limits before the other ones reach their resource limits. And this could be true within an application. It often is. It's especially true outside an application. Maybe like I'm handling this request from a client device and I have to like call to an upstream service, and that upstream service needs to call to DynamoDB, but the DynamoDB table is underscaled because we just got a load spike, which means that Dynamo can't respond very fast, which means the upstream service can't respond very fast, which means that I can't handle this request very quickly, which means that the clients need to stop asking me to handle requests. And that chain is basically back pressure. And if you mess that up at any point, you basically lose the link in the chain, then you're going to have, it's going to be like a dam that's overflowing, right? Like you need to have that that control valve. You need to have that spillway to basically propagate a 302 back to the clients, or or a 503, I think is the error that you actually want, or other things like that. You need to get things to slow down and speed up elastically, and this is a very, very, very important property. It's important for something else, which I'll show you in a second as well. The problem is Future doesn't help you with this. So futures are handles, for the most part, to results that are being computed, present tense. Okay, stuff is happening. It's very difficult for you to get a future into your hand and then change your mind and be like, actually, hang on, don't do that right now. Wait just a second because I'm not ready for the result yet. And the result's going to come in and it's going to sit in memory. And if you just sort of kicked off 100,000 futures, but you're only ready to handle the results for the first 1,000 of them, well, the other 99,000 are going to be like sitting in memory waiting for you, which is going to cause a problem. Again, the dam kind of overflowing rather than the spillway, or just slowing down the flow of the river, which is really what we want. It also means that load shedding has to be done very carefully and explicitly. And this is, again, something that people don't often think about until you operate a system at extremely high scale and you see it fall over. But an example of this is like at one point I was working on a service that one night went from about 1 million RPS edge traffic to about 100 million RPS in a matter of minutes. It had that kind of global spike. This kind of spike is insane, right? Because even if it's possible for you to scale up your compute cluster and like scale out in multiple regions to the point where you can absorb and correctly handle and respond to that kind of traffic, there's absolutely no way you can do it instantly. It takes time to provision instances, especially if you have to provision new VMs. It takes time for those JVMs to become warm. Like this, it cascades down the line. And in the meantime, you have to make sure that your application does not break. And running out of memory or crashing a system, or even worse, running out of file handles is the opposite of not breaking. That will degrade a system and you have to kill the node, which is like the opposite of what you're trying to do when you're trying really hard to scale out to absorb a giant spike. So this is what load shedding is for, right? Ultimately, you have to have a stopgap, which is like, okay, I can't handle this connection. I have to drop it on the floor without using any scarce resources at all. Not just little bits of scarce resources, but zero scarce resources. There are ways of doing this. TCP gives you really nice mechanisms for doing this. The kernel gives you nice mechanisms for doing this, but we do have to take advantage of them. We have to propagate that back pressure signal back to it. Future gives you nothing that helps you with this problem space, because ultimately Future is fundamentally a push model. Like you sort of run a computation, you invoke a callback that causes a Future to run. Back pressure really requires the opposite model, right? It's like, okay, I'm doing a thing, and when I am ready, I will ask you to perform your computation and invoke my callback and move forward. That type of pull model is really what you need. Future doesn't do that, and none of the systems that are built on Future do that, which means you have an entire ecosystem when things built on top of Future, basically, which is vulnerable to these types of problems. And as a user of things within that ecosystem, you have to be hyper aware of it, or it's going to bite you in production, as it pretty much bites everybody. And I know it's bitten me. So ultimately, effect systems come from the observation that this doesn't have to be just good enough. Like, we don't have to settle for this situation. We can take it a step further. And this is basically what this talk is about, is evolving Future into something more, into a better version of itself. So really what we're trying to do here is we're trying to have all of the benefits of Future, just like sort of wrapping up callbacks and things like that, but with some other benefits as well, okay? So benefit number one that we really want, deterministic control flow, okay? If I say A, then B, then C, I want that to be the order in which they evaluate. And I want to be able to fiddle around with values and things like that. I want to be able to refactor my code. And as long as I put it together, constructed it in such a way that it's still A, then B, then C, then I want that to be deterministically what happens. And if I want non-determinism, like I want like two things to happen at the same time, truly in parallel, well, I'll ask for that. But if I don't ask for that, don't just give it to me randomly. Like, I want things to be very under control. I want first-class support for cancellation and interruption, really. This is super important, because without this, you cannot implement timeouts. Like, you can't implement connection timeouts, you can't implement request response timeouts, you can't do anything related to this extremely fundamental problem that literally everyone has. You can't solve that problem without first-class support for timeouts, or for cancellation rather. And it has to be something that the runtime gives you. So we need to have that. But this brings us to needing to have first-class support for resource management as well, because you can't really say like, oh, I'm going to time out this connection without also providing some way of cleaning up that connection, because you can't have resource leaks. Again, scale always comes back to managing scarce resources, right? File handles, as part of the connection, and the memory associated with managing it, those are scarce resources. We have to make sure that they are cleaned up reliably and deterministically when we time out. And that process of doing it has to count towards the load on the system, because it's work that the system is doing. And when the system is under load, it has to pressure its downstream, or pressure its upstream, depending on the perspective of the river flow, to make sure that that upstream slows down. So back pressure by default is really what you want. Like, I want my system to be safe. Because really, when you're saying you don't want back pressure by default, what you're actually saying is you want the default semantic to be, I will run out of memory. I don't think anyone would actually phrase it that way, but this is what you're asking for if you want back pressure to be an opt-in semantic. So back pressure on by default is really, really a minimum bar here. We have to have this, which means we have to be a pull model. It means a whole bunch of other stuff. We have to be incremental with our memory use, things like that. But what we get for doing this, and for all of the caveats that come along with it, is we get things like free load shedding. That means that when you have that service, like I did, that went from 1 million global RPS to 100 million global RPS in a blink of an eye, that service is fine. Even if I didn't consider that situation explicitly, because I certainly did not consider that situation explicitly, even if I didn't think about it, it's still going to be okay because the service will just gracefully shed the load. And like clients are going to get errors. Like it's obviously not going to work correctly, but the system will protect itself by default. That's the huge benefit that you get right here. It also gives you protection on your other scarce resources. So memory, for example, if you do this correctly, then you never have that situation where like, oh, I started a future and like it's callback completed, but I'm not actually ready for the response yet. So it's just going to sit in memory forever and then like leak, or like, I'm going to have like these huge sort of working sets that are completely unnecessary. I'm reading a file or I'm reading a streaming HTTP request, and like I have to think about like whether or not I have this in memory at any given point in time. Like none of that matters anymore, because if you do this correctly, it's all related to back pressure, right? It's all related to this protection of scarce resources. And we said that we want to do this out of the box by default without any user input. It should just happen and you shouldn't have to think about it. And these are some of the fundamental tenets that underlie effect systems. So coming back to an example that I did earlier, this is fine, right? Like if foo, bar, baz, and quux are actually IO rather than being future, there's no problem with this program whatsoever. We can do stuff like this like crazy. I could pull all of them out into values and it's fine. I could refactor this. I could split the code apart. And as long as I construct it back together again with the same sort of sequentialization, I know for a fact that the program hasn't changed. Now, this looks really stupid on a slide. Really, really stupid on a slide. And it is stupid because we can figure it out. But like, imagine this at the level of a system. Imagine if bar is actually some really complex module that like goes off and talks to databases and talks to services and other things like that. Imagine if foo, bar, and quux are all these super, super complex things. I don't have to care that they're super, super complex things. I don't have to care that they might interact. I don't have to care about any of that because I know that these programs are the same. And that is the power of refactoring, like really, really power. That's the power of algebra. And we'll talk about that a little bit later. But even with that kind of hand-wavy assertion, I think that's still like something of an uncompelling example. So I have a slightly more compelling one for you. And that's just retries. I think this is a really great example. Like you'll see this going around a lot with effect systems because it's just a very like clear way of explaining the power that effect systems bring to you. So I can write this generic function, retry for any value of A, for any type A, that takes an action, IO of A, and we'll just retry it up to n times until it succeeds. And if I get an error, I'll just try the action again. This works for any IO of A. I don't have to, it could be talking to a database. It could be just performing some sort of in-memory computation. It could be writing to a file. It could be, any of these sorts of things. It could be talking to an upstream service, right? I can do retries for all of them using this one function. I don't actually have to care when I'm defining this function. So the semantic of retry can be split from the semantic of what is happening. You cannot write this function for future. There's a whole bunch of reasons why, but you cannot write this function for future. And because future doesn't represent an action to be run, it represents a handle to the result of an action which is probably already running. And that difference is quite profound. IO is a handle to an action to run. We can run it as many times as we want. We can not run it at all. We can twiddle with it. We can change the way that it runs. And you can make this example even more powerful still without peeking into action, right? So most of the time you don't want n up to n retries. What you actually want is some sort of exponential backoff semantic, which you can do in like 6 lines of code, right? So this is basically what it looks like, a pretty straightforward exponential backoff where we're given the initial seed, we're going to back off n times, and we're just going to like, every time we're going to back off between a random value between 0 and the current number of milliseconds, we'll double it each time. This is super cool, right? And you can just throw this type of thing together, and then you can apply this semantic to anything. So this is a generic retry function that works with any action, doesn't matter what. The action could have resources associated. It could have other things, and there could be other things wrapped around us. It doesn't matter. So for example, right, like maybe the action that we're talking about is making a request to some, upstream service, okay? So that action was going to have like IO of results as the type because it's an action that returns, the results of that request. Well, we can wrap that up in retry to give ourselves an exponential backoff semantic. We want to keep trying, if this upstream service gives us an error, and keep trying up to some bound. But maybe at the same time, we're within the context of our own request response loop. Remember that sort of request handler, scatter, gather type archetype I gave you at the beginning. So we want to make sure that we respond, no matter what, we respond to our caller within 1 second. Okay, that's just our SLA. So we just throw .timeout around the whole thing. And if we time out, we have to make sure the retry gets canceled. We have to make sure that if the request is currently outstanding, we close the connection. We sort of free any memory associated with this. And you know what? It works exactly like this. And in practice, all of these things, of course, are spread throughout the code base, right? That request response timeout is probably closer to the web service, probably closer to the endpoint handler. This sort of retry exponential backoff type thing might be in a library off on the side. The request that we're actually making to the client might be defined by some client SDK that we were handed by another team. All of those sorts of things, we can bring them together, and we don't have to care about their implementation, about their internals, because we understand that the control flow is deterministic. And we understand that we have these powerful primitives like resource management and cancellation that all sort of work together to give us these types of properties. This is completely working code. And by the way, I do want to make sure it is understood that there is absolutely nothing in any effects system framework which is hard coded to these types of cases. Like I kind of made fun of exponential backoff because it is an example that like we tend to bring up a lot. But there's no exponential backoff routine inside of Cat's effect. There's no timeout routine or anything like that. It's actually implemented in terms of more fundamental primitives. They're all implemented in terms of more fundamental primitives. Effect systems are just very, very general. So I can give you a bunch of use cases today where this makes sense. What I'm more interested in is making sure that it still makes sense for the use cases of 10 years from now. And I'm very confident that that's the case because it's such a simple and core foundation. So I've been talking a lot about resource management. Let's actually see what that looks like, because resources are very complicated. And obviously there's Martin's student's proposal about sort of like tracking capabilities and putting a form of linearity within Scala 3's type system. This is how effect systems address this problem, right? The idea is basically this. You define the actions which open and close a resource, right? And then glue these actions together in such a way that if you open the resource, you will always, always, always close it, even if you are timed out, even if you're in an error case, whatever, does not matter, as long as like those things are married together. This allows you to separate your logic, okay? Because the holy grail here is you want to be able to define the logic which shows how to construct a resource, sort of make a connection or open a file like that, open a database, like those types of things. You want to be able to define that logic in one place and then sort of hermetically seal it and not think about it again. And then elsewhere, you want to use that connection. You want to use that resource. You want to take advantage of it, and you want to compose it together. And maybe you might want to throw other semantics on top of that, like the timeouts that we saw, or retries, or things like that. Cool. But like, you need to have the guarantee that the resources will be opened and closed correctly, and you just can't think about it. This separation is achieved through these types of mechanisms, and this removes coupling across resource and application lifecycles. So you can kind of think about the different parts of your application independently. You don't have to think like, oh, there's this future that like sets up the database connection, and I need to make sure that it ran and only ran once, and then, oh crap, the connection is open now, so I need to make sure I close it somewhere else, but there's this one case that I forgot about that happens sometimes in production, and so now I'm leaking connections, and now like the system crashes, or I get like a 9-figure AWS bill or something like that. Like, I don't have to think about those problems at all when I use an effect system. They don't even enter my head, because as long as I follow this rule, it's going to be fine. And the framework basically prevents me from breaking that rule. This entirely eliminates a whole class of bugs. You don't have resource leaks at all anymore. And it's hard to describe how freeing that is. Like you just don't have to even think about it. So you stop thinking about it. You can think about other things, and that's the power of it. So here's an example. Let's say that we have this function that sort of makes a connection given a JDBC URI. And then when we make a connection, which is conspicuously enough of type connection, we can call close on it, and close will return an IO of unit. And what that IO of unit will do is close the connection. We can marry those actions together using something called a resource. And what resource is another monad. It's sort of built on top of IO that gives us these types of resource threading semantics, allowing us to talk about resources as a thing that might have sort of unbounded scope. Like here, return a thing and then do whatever you want with it. That's kind of the idea of resource. Here we sort of have this function connect to the database and give me a resource of connection. And as long as this is the way that we connect to the database, we don't have to think about closing the connection. We don't have to think about connection leaks or anything like that, because it's going to work for us. So if we wanted to add some extra semantics like connection pooling or sort of like multiplexing on a singular connection, like other things that I guess JDBC can't really do, but pretend with me for a second, like those semantics could be added in the connect function without touching any of that downstream code where we actually use the connection to run a select and run an update and other things like that. At the end of that block, at the end of the sort of thing down below, when we're done using the connection, it will be closed. It will be closed for us, and we didn't even have to think about it. There could even be other resources that get folded into this block, or we could be folded into another resource block. And those resources will also be managed with the same things. And again, you still have those same guarantees around cancellations, timeouts, memory safety, all those other things still work with this. We're just building on top of that same functionality. An example of how the composability here really helps us, imagine if we have multiple read replicas on our database. So we've got replica 1 and replica 2, and really when we make a connection, we actually want to try to connect to both of them at the same time, and whichever one responds first will shut down the other connection because we don't need it anymore, and then just hold that first one open. Well, you can do that in a single line. And we can build that on top of the connection thing, and that code that we wrote earlier, which uses the connections, doesn't even have to know that we did that. So this talks like the maintainability aspect that effect systems bring to you, which is the fact that you can refactor your application independently in these different places and make these changes without it being a problem, without tangling logic together. All of these things give rise to ultimately a really powerful ecosystem, both of applications and of libraries. Because when you're starting with this extremely small and composable functional surface area, it gives you this very reliable foundation on which to build complex functionality, right? We saw an example of that with sort of retry, but the type level ecosystem is sort of replete with examples of sort of composable things that sort of layer on top of each other really nicely, like streaming and web frameworks and like Redis clients and Postgres clients. Like the list goes on and on and on and on and on. There's so much stuff that you can do when you can trust the layers underneath you to be very, very foundational and very, very strong. When you can no longer have to think about some of these extremely common problems like resource safety, when you no longer have to have these caveats and this coupling, you can talk about things in terms of components. It is really powerful. And honestly, I think that because of these things and some more things that I'm going to talk about in a second, I think that effect systems really represent the next generation of reactive programming, like the reactive paradigm. It moves the state of the art really substantially beyond callbacks and coroutines, like beyond this simple sort of, async promise future, like beyond callbacks. Like it takes a significant step forward and gives us a lot of power that we just can't get otherwise. And this, by the way, I'm going to take a second to sort of raise this point. This is why I don't really care that much about Project Loom. Because what Project Loom does is it obsoletes future. It doesn't obsolete IO. Project Loom gives you a really nice solution to sort of the base coroutine problem, like the problem of sort of linearizing callbacks into sequential flows. But it does absolutely nothing for resources. It has absolutely nothing for timeouts and preemption or any of the other things. And it doesn't give you any sort of mechanisms for talking about control flow at these higher level things. So you simply cannot, for example, implement a retry combinator on top of anything that Loom gives you. Like it's just not going to work. And you're basically going to have that whole set of problems all over again. So Loom is cool, but I think we've kind of moved past it. Like it's a little bit behind us at this point. Effect systems set the guardrails for safer and more composable applications and libraries, and ultimately they constrain the problem space to allow for deeper integration. Now, this is a funny thing to say, right? Like normally when you're talking up like a new paradigm, which is what this is, you try to say things like, well, this empowers you to do this, or this like opens up this functionality, this gives you these things, this allows this that you couldn't do before. And it does. But it does that ironically by sort of locking things down and constraining things. And in the process of constraining things, opens up more functionality than you probably even considered possible. And this is the point that often gets missed with effect systems, is the deep runtime integration that you can get out of them. I've spent all this time talking about, well, there's all these problems and like future's annoying and like, oh, timeouts here, like, you know, stuff like that, right? These are the cases that you can get, really talking about composability and reasoning about your application and sort of hand waving at it in slides. But I want to take a second to talk about how it can actually be implemented in better ways and how we can actually get better performance than what you can do by hand because of how effect systems constrain the design space. So here we go. So effect systems are built on top of a core algebraic model, which is sort of very simple, very composable pieces that sort of behave together in these very discrete ways. And what it does by doing that, we get very, very comprehensive insight into what the program is doing. We understand what the program can do at any point in time, or rather more precisely what the fiber, what the sequence of actions can do at any given point in time. We understand the patterns that are likely because we have constrained those patterns. We have, and there are various examples of this, right? Like one of them is blocking, right? We talked earlier about how blocking I/O is a big problem because it eats up threads. Well, blocking I/O is in practice unavoidable, especially if you're talking to a file system, because most file system access patterns or access mechanisms, even at the kernel level, are not asynchronous. There are other problems as well, such as DNS clients and things like that. Like these are kind of fundamental facts because that's what the operating system gives us. But effect systems push you really hard to declare these blocking regions, which in turn means that the runtime can understand what's going on, understand that the user is declaring certain things, and it can optimize it around it. And we do this in a number of ways in Cat's Effect. One of the most notable ways introduced in Cat's Effect 3 is the work stealing fiber runtime. So remember, all the way back an hour ago when we were talking about CPUs and we were talking about sort of cache affinity and page faults and things like that, we basically put forward the claim that page faults are this really costly thing that we need to be avoiding by trying to map our threads very precisely down to CPUs. Well, because of how declarative the control flow is in Cat's Effect, we can take that a step further and we can say not only are the threads mapped down to CPUs by having a fixed number of them, we're also going to map the fibers down to CPUs, where the fiber basically represents like a single request response cycle that you're doing, that type of thing. Well, there's a lot of advantages to that, right? Because a fiber is semantically kind of the same idea as a thread. It's going to have, each step of it is probably going to use the same memory that the previous step used. So trying to get that mapped down to a CPU works really well. And this is exactly what the work stealing runtime does. So in practice, your page faults drop very, 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 very low here, precisely because we're able to have this very deep visibility and insight into what the program is doing. In practice, when you look at the scheduler overhead specifically, this is between 1 and 2 orders of magnitude faster than a conventional handwritten disruptor pattern. Like, that's not a typo. I literally mean 10 to 100 times faster. These are real performance wins that you see in production. This is real efficiency right here. And again, a lot of it comes down to minimizing those page faults. We can take this a step further, though, right? One of the things we can take advantage of is the fact that we know that there's a fixed number of compute threads that are going to be doing everything. And any work that gets triggered as the result of some other action, callback, timer, or something like that, is going to have to come back to those compute threads, which means in turn that we can do strategies for executing timers, which are ubiquitous in network programming. We can do strategies for executing timers that are more efficient because we understand that we're not increasing jitter or like decreasing fidelity or things like that. So one of these techniques is called cooperative polling. This is something that we're working on and hoping to get released in Cats Effect 3.4. And the results are pretty breathtaking. Like the amount of performance improvement that you get in any case involving a sleep, which remember retry involves a sleep. It's ridiculous how much performance you can get out of it. But you can, it doesn't just have to be about performance, right? One of the nice things about Cats Effect is this thing we call test control, which allows you to basically sort of get your hands deeply into the runtime and change the way that the program is going to execute without changing the program itself. And one of the most obvious places where you need to do that is anything having to do with time, right? So that retry function, imagine you had written that, but now you want to write a unit test for it. Well, unit tests for like exponential backoff are notoriously fragile, especially in CI, because you're testing sleep, right? Well, with test control, you can just write a unit test. So this is real working code, right? And this shows an example action that's kind of designed to sort of simulate this. I'm doing this with munit, by the way. And this action basically is like going to fail by throwing an exception for the first 3 times, and then it'll succeed on the 4th try. And we just want to prove that like it works, and then you sort of have this exponential backoff semantic. We could write a different test which shows that the right amount of time has passed. But note the amount of time that we give to the retry function. We're asking it to back off for a minute with each retry cycle. So that would be very slow if we actually wanted to test that. But with test control, this test runs in a few milliseconds. Because what ends up happening is it's able to deeply introspect the runtime and make sure that all of these sort of things are aligned up correctly. Again, because of this sort of constrained model, which provides us with a lot of this insight. There's a lot more stuff in here as well. We definitely don't have anywhere near enough time to go through all of it, but hopefully this gives you a little bit of a taste of like what you can do as a runtime framework, as Cats Effect, when you understand that the program is written within this sort of very sort of composable and rigid model. And the benefits that you can get as a user from this are quite profound. I think we're past the point where we should be skeptical of effect systems in the wild. Effect systems of all types are deployed by some of the largest companies in the world. Tokyo, which is what I brought up earlier, is literally sponsored by Amazon, and a lot of AWS takes advantage of it. Things, even just confining our focus to Scala with the sort of Cats Effect and Zio, there's a lot of household name services that are powered by effect systems. I mean, I work at Disney, like and you know that is a household name service. We're hiring, by the way. But you know, these things are proven at scale, and they are proven to be extremely beneficial. Now, there are some assumptions that you have to make in order to work with these things at scale. Like the biggest assumption is basically the number of IO allocations is linearly proportional to the number of IO actions that you perform, like the sort of network calls or file system calls or things like that, right? This is basically the same way as saying that your application is IO bound, like on a fundamental level. Like you're a microservice, for example. If you're doing something which is like, I'm doing scientific computing and I'm just like strictly compute bound or something like that, these things are a little bit less compelling, like the optimizations don't fit as well. There's some other cases where they don't work as well, but these don't really come up in practice. In practice, for the types of applications that 95% of us are ever going to write, these types of things work incredibly well. And really, it's beyond hypothetical at this point. Like the allocation overhead is demonstrably irrelevant. And I think this really proves the thesis that FP in the large is the right way to do it, because you get the benefits of the composability and the performance. You know, the performance effects of all those allocations don't really matter. FP in the small is much less exciting. So I'm almost done, I promise. But I wanted to talk just a little bit about what are the constraints that get imposed by effect systems on the applications that you write, on the types of code that you can write. What are the rules that you have to follow? And if you follow those rules, you get all of these benefits for free. So the rules basically fit on a slide. So rule number one, take every single side effect, anything that affects sort of like things like a network call, or like a file system, or anything like that, and wrap all of them in delay, async, blocking, or interruptible, whatever the most appropriate one is. And there is a specific appropriate one for every single one of these cases. So do this, right? Thing number two, use bracket or resource for anything that can be closed. So this is what gives you your resource management. If you follow this rule, this is what gives you the composability of your resources. Never, ever, ever block a thread outside of blocking or interruptible. Inside of blocking and interruptible, it's safe. Still not a great idea, but like safe, and sometimes you have to do it. And as long as you follow this rule, your runtime is going to be still very good. Use IOApp. Don't write your own def main. And by using IOApp, you can avoid calling unsafe methods. And as long as you avoid calling unsafe methods, anywhere in your code base, you have the guarantee that all of these properties that the runtime sort of understands your application, and like all these things that you want to get, those guarantees are in place as long as you follow these rules. And in practice, this is a very pleasant set of rules to follow. Like it's not at all difficult to do this. And like I said, the benefits you get are massive. So in conclusion, and I really could talk about this for hours and hours and hours, but we're going to wrap it up here. Effect systems are very, very well motivated. There's a lot of pragmatic thought that has gone into the trade-offs that are chosen, and I think they really do represent a paradigm shift beyond future. Project Loom, which everybody is talking about, replaces future. It doesn't replace IO. Like it sort of it covers that previous generation of thought, and for some applications that's going to be fantastic. But for other things, it's not going to sort of match what we have here. The performance really is fantastic, and in practice, it's a lot better than the hand-rolled alternatives. Even though you're taking on these excess allocations, these excess IO objects, things like that, and these frameworks are the foundation for a set of very, very powerful ecosystems that are really just getting started in terms of what they can do, because they're built on this extremely strong foundation. So I've gone longer than I expected to, because I sort of ate up some of my question time. But I think we might have a little bit of time left for that. Thank you very, very much for your attention and your patience.
Hello, thank you. A lot of people are clapping. I hope you can see the reactions. They were actually, engaging with you during the talk. I'm not sure if that was visible for you or not. It was visible for me. And actually, I didn't see a lot of questions, because when there were questions, other people on chat were able to answer them. So the conversation kind of was flowing on its own. But definitely a lot of messages, and people, consider different things that are related to the topic, including echo streams. And there were a lot of, conversation about that and other things. So everyone, please post your questions. We will spend a little bit of time answering them. So for example, can you please use a hash table or something, hashtag or something? Hash table, I don't know. We don't use that.
It's been a long day.
Yeah. So use hashtag so that I can figure out which questions are where. So the first one, I guess, is do you use Scala 3 in production? How do you think Scala 3 will impact CAT's effect?
That is an awesome question. So no, I do not use Scala 3 in production. I know a couple of teams that have experimented with it, and I think the results have been quite good. I think companies as a whole are, including ours, are being, cautious with moving into it, especially because it's fairly early on, which I think is fair. the second question being related to like how Scala 3 will affect Cat's effect, in the short term, not very much, because we have to maintain this backwards compatibility with Scala 2, and we've sort of committed to cross-compiling between those. So we can't really take advantage of any of the niceness. However, there is a plan in the works in Cats 3 to break compatibility with Scala 2 and be sort of Scala 3 only. This will be years in the future. And when we do that, the benefits will be really significant. I think probably the most noticeable one that users will see is like you won't have to do syntax imports anymore. Like you'll get monad, monoid, syntax, like whatever you want, basically because it's just paired to the type class. So it will work in the way that you always wanted it to work, basically. There's a lot of benefits like that. And Cat's effect will inherit those and sort of carry them forward.
Yeah, and of course you'll do that safely and gradually, so everyone will have time to, improve their code base so that it could support that. So the next question: why do you think an effect type hasn't been put into the Scala standard library, while async types like future have been included there?
A great question. Effect types and effect systems have been evolving fairly rapidly over the last couple of years. And I certainly would not be so presumptuous to claim that we are at the end of that evolution. I'm sure there's more that we can discover. Putting it in the standard library kind of freezes it in a sense. And the only benefit that you get is you get like a shared vocabulary, right? It would effectively just kind of like pick a winner on like how this stuff is going to work. So if you want to get that benefit, basically what you would want is an abstraction in the standard library, something like Cat's effects type classes. But even that has been something that's been iterated on and developed, and like new things have been learned over the years. So I think it's just not there yet. I think we're at the point where it's mature enough that I really think it is the right way to write applications in production, and especially at scale right now. But I wouldn't put it in the standard library right now. Let's give that some time to really sort of bake down.
Okay, then we have a couple of jokes that you are Disney's true mascot. And it's kind of unfair advantage on the Harvard market. Well, yes.
It's in my contract to wear the ears.
Nice. All right. Then we have a question. When futures are not cancelable, etc., how does io.from future actually work?
Yes. Jakob answered that, but I'll answer it as well. It is, they are uncancelable in that case. So basically that little, what will happen is, if you kind of imagine evaluation as a line, right? And like there's a series of IO stages that make up that line. If you try to cancel from the outside at any point along this line, IO will try to interrupt the current stage and it will sort of like cut off the line. That's the idea. But if the current stage can't be interrupted, like IO from future, then the interruption will basically just wait until it can cut the line. So it'll still interrupt it as fast as possible. It'll still provide you with those benefits. And it will actually back pressure the cancellation so that you don't have these sort of leaks of futures or other things like that. So it will protect you from that type of scenario.
All right. Then Thomas is asking, how would you rewrite something like object input stream into a non-blocking IO program?
Yeah, I mean, input stream is sort of fundamentally a blocking interface. And your only option there is to declare to the runtime that it is a blocking interface. It's not a great situation, but it's better than nothing. So for that, you would use blocking, or more ideally, interruptible. And what interruptible does is it tells the runtime, hey, this is going to block a thread, so make sure that you don't starve the pool, like adjust things for that. And number two, make it cancelable. So, and it'll forward the cancellation on to like JVM thread interruption, which actually allows you to do some nifty things, especially around like blocking IO and like object input stream.
Yeah, and Jacob is thanking everyone who works on Cat's effect. And yes, I agree. And I join him thanking and saying that you're truly awesome and great inspirations for the entire community. That's been really great.